Statistical aspects of learning. As a matter of fact, in the last class itself we had introduced this topic, on completion of our discussions related to the associative memory, and there towards the end of the class we were deriving an expression that involved the cost function. Okay. Our objective in the statistical aspect of learning was to get an approximation function using the neural network, okay, and that approximation function we are calling as f as a function of x and w, okay, that closely approximates the regression function which is f of x. So, we were interested in finding out that how much of fitment error is there between the realization of actual f x and the f of x w which you are realizing out of the neural network, and we were deriving the expression for cost function. So, starting with the definition of the cost function, where we were taking it as the expectation over the set of target patterns, okay, of d minus f x comma tau, okay, the square of this. So, expectation of this squared quantity over the training samples, that is what we were calculating. And just for the ease of our expressibility, what we did was that this d minus f term we had broken up into two, okay, so that we introduced the minus f of x vector, okay, in the linear regression form, in the regression function form, which we subtracted and then we added, okay. So, that idea was to separate this term, that is d minus f x, and to have f x minus f x comma tau, okay, as separate entities. So, this term d minus f x was our epsilon, that is error, and f x minus f x tau, that was nothing but the deviation that we have between the function, between the regression function f x and the neural network realization, okay. And we substituted this d minus f expression into the original definition of this C w, and we got as C w this expression, okay. In fact, we had got, naturally this being a sum of two quantities, if you square it up, since you have to do a square of this d minus f term, if you square it up, you get an epsilon squared term, okay, which is representing the intrinsic error. So, basically this is nothing but intrinsic error, okay, that is nothing but the error that we are having between the f x and its the mean expectational error of f x, that is what we were representing by this epsilon. And then we had the square of this quantity, okay, without any problem, and we had a term that involved a multiplication of epsilon with this, okay. Now, this term will equate to 0, okay, and in fact that is what we were discussing towards the end, okay. This term will equate towards 0 simply because the intrinsic error epsilon is uncorrelated with respect to both f x and the neural network realization function f of x tau, okay. And since it is uncorrelated with respect to both of this term will equate to 0, okay. So, we get C w as a sum of these two expressions, and out of this term is certainly not varying with respect to w. So, if we are doing any optimization with respect to the weight, okay, then this term will not contribute, and what contributes is only this one, that is this half of e over tau e over t, okay, and it is the expectation or the average operator over the training samples for this f x minus f x comma tau, okay. In fact, that is what we are interested in finding out. So, existence of this term effectively is the we can call this term to be the natural measure of the effectiveness of f of x tau as a predictor. What is after all the f of x tau? F of x tau is nothing but the predictor of the system. Okay. So, how effective this f of x tau is as a predictor, okay, that will be represented by expectation over the training samples t of this quantity f x minus f x tau, okay, this term square. So, the natural measure of effectiveness we can write in this manner. The natural measure of effectiveness of what? Of f x comma w as a predictor. So, the natural measure of this is L av, okay, L average. So, L, I mean we are indicating it by L, and the argument of L will be f of x, since I mean we are predicting this f of x using f of x w. Okay. So, this will be E over the training set T, okay, average of this f of x minus f of x comma t, this term square, okay, expectation of this. So, this is the natural measure of effectiveness, and now let us invoke the original definition of our f x. After all, what is f x? We had already learned that f x is nothing but the expectation of the random variable d of d given the random variable x is equal to one realization, which is x vector. So, f of x vector is equal to expectation of random variable d given random variable x is having an instance x vector. Okay. So, now if we use this, okay, then the L av of this, I am not writing the full thing once again, is equal to E t of, instead of f x we have to write it as E of d given x vector is equal to, the large x vector is the random variable and the small x vector is an instance of that. Okay. So, this one, okay. So, expectation of this term, okay, minus f of x comma t, okay, as it is, and the square of this. So, simply f x being replaced by this, nothing else. Okay. Now, what we can do is that, I mean this is the average value of the estimation error between the regression function and the approximating function evaluated over the entire training set T. All right. Now, what we can do is that this term we can rewrite in a more convenient form. What we can do is that this E of d, I mean that is a term which is there within this E t expression, E of d given capital X vector is equal to small x vector, okay, minus f of x vector comma t, okay, that can be written again as a summation of two quantities. What? E of d given x equal to x vector minus E t of f x vector t. And what is this? Let us just carefully look at this term. By saying E t of this function, what I mean to say is that this function is what? This function is our the function that we are realizing out of the neural network, okay. And we are averaging it over the training set, because this function will have different instances of realization, is not it? Because we have got a large training set. So, for different training patterns it will I mean have different functions, okay, realized, and we are only taking the average over the training set. So, that is why we are just bringing in a quantity which is nothing but the average of this realized function, averaged over what? Averaged over the training patterns T. Okay. So, we are just introducing this term. Okay. So, that is what we have already subtracted from this. So, what we have to do is also to add up this term. So, now in order to compensate for this, we add up this term again, which is E t of f x comma t, okay. This one minus f x comma t. Okay. So, two quantities, sum of two quantities, this plus this. Now, the question is that what is the interpretation of these two quantities? What is this one? E of this expression, that means to say nothing but the regression function only, the definition of the regression function, minus the averaged value of this one. What can you call it in statistical quantity? Anybody can suggest a good name for that? E minus the expectation of the realized function, not the variance. Variance actually, okay, I mean we will come to this. Actually, this is a summation of two quantities, right? Okay. Let us put it into this expression, because after all we are finding out this L average, isn't it? So, we are finding out the natural measure of effectiveness. So, to find out the natural measure of effectiveness, we just express this quantity as a summation of these two quantities, and since we have to take a square of these, we have to take a square of these two summed quantities A plus B. If you take this to be A and if you take this to be B, you are doing A plus B whole square. So, naturally it will lead to again three terms. One will be the A square term, that is to say this minus this whole square. Okay. This minus this effectively is what? This minus this, I mean that is expectation of d given x is equal to x, that means to say the regression function realization minus E t of f x, that is the averaged value of the realized function and the actual function. The difference between the two is nothing but the bias, that is the bias term. So, if you are just putting it into this expression, you get a quantity which is nothing but the square of the bias term. Okay. So, you get a square of the bias term, and also you get the square of this quantity, and this quantity means what? This quantity is, yes, correct, this quantity is variance, the second quantity. Why? Because we are realizing a function f of x t. Okay. Now, for different patterns in the training set, our f function realizations are becoming different, but there is also an averaged f function realization, which is this. So, this is the averaged f function realization minus the f function realized out of a specific training pattern. Okay. And if we just square it up, okay, then that leads to the variance term. So, when I am expressing this quantity, the quantity written within the bracket of this expression as a summation of two quantities, then the first term of this is the bias term, and the second term of this happens to be the variance term, right. So, or bias square and variance term, I mean if we are putting it this way, and also there will be a term, okay, which will be a multiplication of that bias and the variance, and since they are independent of each other, okay, so that will again, I mean since we are taking the expectation operator finally, that will evaluate to 0. So, in effect we are going to have the L expression, the L average expression as follows. So, we can just write down that L av of f x vector comma capital F x vector t. Okay. So, the natural measure of effectiveness will be nothing but the square of the bias term, which we can write simply as b square. As an argument we can only put the weight w, because after all that is what the only variable is, okay, and plus the variance term v w. Okay. So, in this case the definition of the bias and the variance is, the bias term is nothing but E t, okay, f x comma t, okay, minus E of d given x is equal to x. Okay. So, this is the bias, and the variance definition is pretty simple. It is E t f x t minus E t, okay, f x t you get actually this thing squared. So, we have to square it up, expectation of this squared quantity. So, this is the variance. Now, the interpretation that we can make out of these two quantities is that this bias term, that is b w, okay, this is the bias, okay, this can be interpreted as approximation error, is not it? Just look at it. This bias term is indicating what? The difference between the actual function and the averaged realized function. Okay. So, this is nothing but the approximation error. Okay. Whereas, the second quantity, that is V w, okay, which is the variance, in effect that is indicating to us the estimation error. So, the two are little different in nature, that is what you should understand. For approximation, we are directly having the error term between the actual function and the averaged realized function, and for the variance, that is to say for the estimation error, it is that to what extent these realized functions are varying for different realizations. Okay. So, that is what the two things are. Okay. So, the yes. Yeah. So, that is right. E tau of this quantity, right? Yeah. So, B we have defined without the expectation. In fact, B is the expectation term only. Okay, I mean, just a minute. I mean, I will clear your doubts. You are getting a B term, which is nothing but the difference between these two. Okay, the expectation of this minus the error. So, was it our original? Yes, our original definition was also this. And in the L average, yes, ultimately it is the expectation of these quantities.
So, it is not L average, that it is not L average. L average will have E of B square, so E of B square. If B is this much.
Okay, I mean, effectively we just simplified this by avoiding that E tau expression outside, E t expression outside, but in effect, I mean, we understand that there are two quantities, okay, effectively, that is something that we have to bother with. That is, one is the bias and the second is variance. Okay. In fact, I mean it can be thought of like this, that supposing this is the, I mean just pictorially, I have, I mean in a two dimensional space, I have a function realization. I mean supposing this is the f x, okay, which is the actual regression function, okay, and supposing we have the different realizations of this f of x w. Okay. Now, say that we have got f x w different realizations out of here, okay, and let us say that this is the averaged f x w realization. So, this one will be our nothing but this is E t of f x w. Okay. So, if you are taking the difference between these two, that is difference between this f x and this E t, that will indicate the bias, all right. Whereas, if you are taking a particular, let us say that this is a particular f x w that you are taking, okay, then you are saying that here this f x minus this f x w, okay, the difference between these two actually will be nothing but the, I mean the L average estimate, that is what we are talking of. So, this one, I mean if I join this, then this will be our bias square plus variance, this term. I mean to the power half, I mean if we are calculating the distance of this. Okay. Now, what happens is that we have to, I mean in order that our f x w is a good estimate of f x, okay, what we have to do is that this f x w should be brought very close to f x. Okay, that means to say that our bias will be less, okay, and also the variance should be less. Okay. Now, it is very difficult to achieve these two things together. Okay. Just simply see that supposing we have got just a few training samples with us, okay, and supposing we have got one realization here, one realization here, one here, one here. So, maybe that the averaged E t that we get, E t of this f x w that we get may be very close to f x, no doubt, but with such few points, okay, our variance will be excessively large. Okay. On the other hand, if we try to make the variance small, okay, then the bias also may be large. So, this aspect is called as a bias variance dilemma. Okay. So, bias variance dilemma means that you cannot simultaneously control both bias and variance, but your objective is to ultimately reduce both, because in the L averaged expression you are getting the bias term as well as the variance term. So, you have to reduce both, but as the kind of argument that I was trying to give you, that with few samples, with few training samples, you can afford to have a small bias, but large variance, or you can afford to have large bias and small variance. Okay. But ultimately, to take care of both bias and variance, okay, what we have to do is to have infinitely large number of training samples. Okay. If we have infinitely large number of training samples, only then it should be possible for us to reduce both bias and variance. Okay. Now, if we again introduce infinitely large number of training samples, that would inevitably mean that our convergence time will be very large. Okay. So, if you want to avoid bias variance dilemma, then you have to accept a large convergence time with the network. And not only that, see, one aspect which we are every time talking about, that is to say, we are simply expressing that you have got a training set, that is to say, you have got a set of xi's where I is equal to 1 to n, and you have got a set of I mean xi vectors here, and you have got a set of di's I is equal to 1 to n, and this xi comma di, this is your training patterns, and you have got such patterns from I is equal to 1 to n. Now, the question is that given a network, okay, which we are actually asking the network to learn, okay, when a network is made to learn with these many training patterns, okay, what is the guarantee that this learning that it is doing is not I mean an over learning or an under learning? Okay. I mean, is there any guarantee that this much of training patterns, these many training patterns, n training patterns is going to be really optimum? Okay. So, that is something that we have to really study, that what is the optimum number of patterns, okay, so that there is no overfitting or underfitting of the data. By again fitting of the data means, again after all what you are giving is that you are giving a set of training patterns, okay, and you are going to fit a function on that, all right. So, that function fitting what you are doing should neither be underfitted nor overfitted. Okay. So, that is something what we have to analyze, and to look into this, before we look into this analysis, okay, there is one statistical tool that we must consider, and that is actually named after two scientists who had proposed this theory, that is Vapnik and Chervonenkis. Okay. These two people, but I do not think that we are required to know the names of both the scientists. Okay. We can simply tell it as VC, okay. And based on their theory, we come to a measure which is called as the VC dimension, and in fact, it is the VC dimension which is a measure of the capacity or the expressive power of a family of classification functions. Okay. So, I can say that VC dimension is a measure of the capacity or expressive power of a family of classification functions. And in fact, based on their theory, if we can compute the VC dimension of any given decision function, okay, because every neural network, as we know, that ultimately is giving us a decision function. Okay. That is to say, I mean, in a very simplest sense, that if it is a binary pattern classification problem, all right, in that case, whatever patterns that we are feeding as an input to that network, okay, will be ultimately classified as the class 1 or class 0. Okay. So, effectively it is realizing that by making use of some classification function. Okay. There is always a decision boundary or a decision function or decision boundary, okay, that will in fact decide that whether this particular pattern will belong to the class 0 or belong to the class 1. Okay. And how powerful these classification functions are, or to pose a problem in a different way, that given some classification functions, okay, what is the number of training patterns that can be fed to the system, okay, so that the classification is possible out of that system without making any error. Okay. That is what we are looking for, and that is why the VC dimension is, that is where the VC dimension has become a very powerful tool for that. Okay. Now, let us consider a binary classification problem, binary pattern classification problem. So, we consider binary pattern classification problem. And there we take that the ultimate decision, okay, it is a binary decision. So, D belongs to a set of 0 and 1. Okay. D can be either 0 or it can be 1, it is a binary pattern classification problem. Now, how are we classifying into the binary patterns? That will be based on some decision rules. Okay. Now, this rules we will be referring to as dichotomy. Dichotomy. So, by dichotomy we mean binary classification function or binary classification function or decision rules. So, in a network we could be having various dichotomies, there could be different decision rules existing in a system. So, a particular network, okay, maybe, or a learning machine rather, could be having a number of such dichotomies. So, let us form an ensemble of such dichotomies. Okay. So, we form a set of dichotomies, let us say this is the set F that we are calling, and this is nothing but a set of functions. Ultimately, it is a classification function, function, rules, whatever way you may call it. So, ultimately the set of rules or the set of functions that we are having, okay, in the learning machine is a set of x w, okay, where this w vector that belongs to a space w. Okay. So, this w belongs to a space w, which could be actually an m dimensional space. Okay. So, this function f is belonging to the m dimensional space w, and this ultimately maps it into 0 or 1. Okay. So, this is the set of classification functions that is possible. Okay. The different classifications, I think things will become more clear when we discuss this with example. Okay. I mean, right now you do not really feel afraid that it is becoming too much of abstract. It is not something that is exactly abstract. I think we will be able to come back to this and understand better with respect to some small examples, okay, very rundown version of examples that we will take. Okay. So, this is what? This is nothing but a set of functions, different set of functions are there, okay, different decision functions, and just an ensemble of that. Okay. So, this is an ensemble. Whatever functions this learning network can have, I put them all together in the form of an ensemble. That is what I have done, nothing very nothing great thing about it, just a representation of that. And now, let us choose the training patterns. Okay. Now, again the training pattern inputs, they will belong to the same m dimensional space. Okay. I mean, given that we have got machines that has got m number of inputs, okay, all our inputs will be basically m dimensional vectors, and as a training pattern we take n such vectors as training patterns. Okay. And we just form a set of such training patterns, very simple. So, we take a set L, okay, which is defined as the set of all the vectors xi's, all right, and this xi's actually belong to a space H, okay, and here I is equal to, so this H is nothing but an m dimensional space. So, this xi belongs to an m dimensional space, and in this case how many training patterns, since we are taking n. So, I is equal to 1, 2, etc., up to n. Now, all the dichotomies are stored in this set, and all the training patterns, okay, or all the input patterns, okay, let us say input, because when I say training, that involves the input as well as the target decisions. I am saying that set of input patterns lie here, the set of dichotomies will lie here, and what are we supposed to do? We are supposed to apply the dichotomies over these set of inputs, okay, and ultimately there will be a function. So, ultimately dichotomy will be a function, okay, that will separate this set L, okay, into two disjointed subsets L0 and L1. So, ultimately we will be getting two disjointed subsets L0 and L1 such that f x0 x w, okay, will be equal to 0 for x vector belonging to L0 space, okay, and it will be equal to 1 for x vector belonging to L1 space. Is it followed? Don't. This one. See, we have got different set of rules on the system. I mean, different set of different decision rules are there in the system. So, I have put an ensemble of all these decision rules. The decision rules are given by functions f of x w. So, the set of all such functions, okay, that forms the ensemble. I have put it in this set f. So far I am only restricted to the definition of that, all right, and then we have defined another set which is the set of inputs. Now, what I said that from this set of dichotomies, okay, let's say we take any one dichotomy out of this, and that dichotomy we apply on this set of L. Okay. So, there will be some of the patterns. Okay. Now, this x will be, so for some of the patterns, for some of the input patterns, okay, the output will be 0, and for some other input patterns the output will be equal to 1. So, for those the patterns for which the output is becoming 0, we are calling that those patterns belong to the set L0, and the patterns for which the output becomes equal to 1, we are putting those patterns in the set L1. So, this L set we are breaking up into two disjointed sets of L0 and L1. Now, it is one particular dichotomy which has just divided it into L 0 and L 1. Now, I take another dichotomy, okay, then I mean some other patterns will belong to L 0, some other patterns will belong to L 1. Let us take a very simple example. I think we should go over to a small example, then that will make it very clear. Let us consider a 2-dimensional space, very simple. I mean, let us not work on the m dimensional space, perhaps that makes our feeling quite abstract. Just a simple 2-dimensional space, okay, so that the inputs are only x 1 and x 2. Mind you, here purposely I did not put any vector notation, because this x 1 is one of the directions, x 2 is other direction. So, there are two inputs x 1 and x 2. Now, in this space I just happen to pick up 4 different training patterns, 4 different inputs, and they will be vectors. So, this is let us say the position of the x 1 vector, say this is the position of the x 2 vector, say this is the position of x 3 vector, and say this is the position of x 4 vector. So, what I did? I only picked up 4 such inputs. So, I have got an L set, and that L set contains what? X 1 vector, x 2 vector, x 3 vector, x 4 vector. Okay. Dichotomies we do not know yet. Let us try to formulate some dichotomies. Okay. Let us take one of the dichotomies which puts up a decision boundary of this nature. Let us say that I have defined a dichotomy f naught, okay, that classifies the patterns as follows. Okay. So, I say that f 0 is a dichotomy, because here lies the decision boundary, means what? That whatever is inside this decision boundary, they will be belonging to the one class of patterns. Let us say that they belong to the pattern 0, and whatever lies outside, that belong to the pattern class 1. All right. So, I take f 0 as a dichotomy, and how is that dichotomy defined? That dichotomy induces 2 disjointed sets, okay, because from L now I will be making 2 disjointed sets L 0 and L 1. Okay. So, dichotomy f 0 will do like this, that it will make L 0 equal to x 1, x 2, x 3, all right, and it will take L 1 as another set, okay, which will be having only x 4, right. So, now you get at least some idea about what dichotomy is. This is one dichotomy that simply specifies a decision boundary, that if it is within this, it belongs to the set L 0, if it is if it is outside this, then it belongs to L 1. So, this way of pattern classification is done. And let us now think of a different dichotomy. Okay. Let us say that instead of this, I pick up this one as a dichotomy. Say now this dichotomy I call as f 1, and f 1 is now again inducing 2 different sets d 1. Okay. This dichotomy can be expressed as 2 sets, one is L 0. In L 0 set we will be having now x 2, x 3, x 4. In L 1 set we will be having x 1. Now, I want to ask you a question. how many such dichotomies are possible? I have got 4 patterns, I mean 4 input pattern. Can you tell me that how many such dichotomies are possible? D0 is, I mean F0 is one of the dichotomies, F1 is another dichotomy, like this I can think of different dichotomies. Huh?
The 4C0 plus 4C1 plus 4C2
not 4 factorial. 2 raised to the power 4 is equal to 16. That is the number of dichotomies that we can have. Okay. Even if you have it like his way, that is 4C0 plus 4C1 plus 4C2, that ultimately adds up to that only. Okay. So, this is a problem from combination, and we are going to have totally 16 dichotomies out of this. Why 16? Because here we have taken a 4 input, or rather the cardinality of this set L. Okay. The cardinality of the set L that we consider, that is equal to 4. Okay. So, that is why for us the total number of dichotomies that is possible is 2 to the power 4, which is equal to 16. Okay. Now, VC dimensions definition says that it is the maximum number in, listen carefully, it is the maximum number of n which makes 2 to the power n number of dichotomies, okay, that can, again I am introducing one term which requires a definition, that actually shatters this L space, shattering, okay, a term that I need to define. Okay. I mean, what I mean to say is that this, I mean here, now that we are getting the maximum number of I mean the cardinality of this set is 4, okay, and it can realize with 16 functions we can fully classify everything. Okay. I mean 16 is the, I mean ultimate number of functions that is possible to segregate this space, or to what we can say as to shatter this space with different type of patterns. Okay. So, since 4 is that number that is doing it, okay, 4 is the maximum, I mean 4 means 2 to the power 4 is equal to that. So, in this case, this particular case, the VC dimension will be equal to 4. Okay. But here the decision boundaries are taken this way, but if the decision boundaries are taken in a different manner, okay, then the VC dimension will also differ, but we will come to that, okay, later on. But let us now formalize the definition. Okay. Now, let us say that delta of L, okay, with I mean suffix we are putting as f. Now, again let us go back to our definition. So, I think that now this definition will not seem to be very abstract, because this is now a set of all dichotomies, okay, and this is the set of input patterns. Okay. So, this is very clear. Now, we are introducing a term called delta L suffix f, okay, and this will denotes the number of distinct dichotomies, denotes the number of distinct dichotomies represented, dichotomies we can say implemented by the learning machine. And let us say that delta f over small l denote the maximum of delta L suffix f, okay, over all L with the cardinality of L equal to L. Okay. So, I think that I need not have to explain this term, this you understand that this is the cardinality. Okay. So, simply speaking, what is that? That if L, small l happens to be the cardinality of the set L, then delta L of f, that represents the maximum number of delta f of L. Okay. So, that it is there. And now coming to the definition of shattering, we say that L, the space L is shattered by the rules are there, that the decision rules are there in F. Okay. If this delta F of L is equal to 2 to the power cardinality of L. Okay. So, if the number of distinct dichotomies existing in the learning system is equal to 2 to the power L, meaning what? In this example, if in the learning system we have all the 16 rules, all the 16 decision rules available with us, then we can say that the input space L is the input space, that is shattered by the set of decision rules or the set of dichotomies F. Any doubts? Requires some time to assimilate, perhaps more examples. Okay. So, we will surely consider some more examples in the next class before the concepts really goes into our mind, but let us only think that here the number of there are a number of rules that you can put into the system, okay, and if your set of rules, okay, actually spans all the different possibilities, okay, if the distinct dichotomies that you are having is equal to 2 to the power L, okay, where L is the cardinality, then that space is shattered, and we will give several shattering examples, okay, and that will be more clear in the coming class. Thank you very much.